So now look at the hack input-output devices, or essentially the keyboard and the screen. Now these are both memory map peripherals, which means that the memory associated with these appears to be part of the main memory or RAM. So the keyboard and the screen have both got memory associated with them, what's given by a particular address. So in fact the keyboard's actually just got it's just a single register, and the screen is represented by a range of addresses. So each pixel can be is addressed by a specific bit in memory. So the addresses for the keyboard and the screen are kind of combined with the addresses in RAM, just so it appears as one big block of memory. Now this is very common in microcontrollers. So we've got flash, we've got RAM, and we've also got various peripherals, and each of these all contain memory. But when to the actual programmer, even though they're physically separate devices with physically separate memory, they're all combined to this one unified memory map. So as a programmer, you don't need to worry about them being different devices. You just need to know the specific address for the device that you want to kind of interface with. So it's kind of shown here. So imagine we've got a whole memory. So this might start at address 0 up to address X, and then the screen memory will be X plus 1 up to, obviously depends on the size of this, that might go up to kind of Y, and then the keyboard kind of Y minus 1. So even though these are separate devices with the kind of own memory associated with them, they kind of combine together into one range of addresses. So the keyboard, so KBD we refer to, it's essentially a 16-bit register at memory location 0x6000. So we looked in here, the keyboard would be at 0x, so that's just one 16-bit register. So it's just a read-only register, so when you read the value of that particular register, it tells us which key's been pressed. So if no key has been pressed, it'll just contain the value 0, but if a key has been pressed, it'll just contain a 16-bit ASCII value of the key. So the numbers 0 to 9 go from 48, are represented by 48 to 57. Then we go uppercase letters, A to Z, from 65 to 90. Lowercase letters, A to Z, 97 to 122. And then there's various kind of special keys, if you will. So this table shows the codes for, say, the arrow keys, page up, page down, and so on. Now the screen. So the screen's got a resolution of 256 rows and 512 columns. So it's kind of shown in this image here. So we've got 512 columns, 256 rows, and then 512 columns. So this is represented by an 8K memory map. So if you multiply those together, you'll finally get an 8K memory map. So this starts at 0x4000. So in memory, this first address will be 0x4000, and then each kind of word then in memory, so this will be 0x4001. So we know the row, so each row has got 512 columns in it. We know we've got, in this hack platform, the words are 16 bits. So 512 divided by 16 gives us 32 words, sorry. So when we look across here, so the first row, the 512 columns will go from kind of word 0, then we'll have word 1, 2, up to 31 in this case. And the next row will start at 32, 33, and so on. So each row is represented by 32 words. Then each bit in those words represents a specific pixel. So we can see in this diagram here, so row 0 comes 0, goes from 0 to 31. Row 1 is from 32 to 63, and then the last row will be from these. And then each particular bit in that word represents a pixel. So if we look at this example here, we can see that for rows in row 0, so this first word will represent columns 0 up to 31, and we can see here, so these two values are 1s here, so that corresponds to these 2 pixels. We've got 2 zeros, these pixels are off, and the next 2 are switched on. And again, then row 1, so that'll be, so words 0 to 31 will represent this kind of first row here, and then row 1 will start at 32, and we can see in this example here, so these, we've got 3 zeros and 3 1s, so that corresponds to these 3 pixels being off and these 3 being switched on. So we can actually address each individual pixel on the screen. So if you want to find the kind of address of the word that the pixel's in, it's given by this formula here. So 16834, that's the kind of starting address of this memory map. So 16384. So we do that plus 32R, that'll tell us which row we're on. Plus C divided by 16, so that'll tell us which particular, which word contains that pixel. So once you know the particular word for the pixel, then we need to set the particular bit. So if you do C remainder 16, that will tell you, so we've got the address, so this part here gives us the address of the word, and then the C remainder 16 will tell us which bit we need to switch on. So a good tip is to remember that -1 in binary is just given by all ones. So for the case of these 16-bit words, we've got 16 ones. So you can just, if you write -1 to a particular location in memory, it'll switch on, it'll turn on all those pixels. So for example, if well, we know the starting is 16384. If you wrote -1 to that memory location, so we've got other kind of memory 16384, if you set that to -1, that'll turn on all these bits, then will be a 1. So it's a quick and easy shortcut for turning on all pixels. And obviously you could, if you set it to 0, you'll turn off all those pixels in that particular word. So there's shortcuts for turning on and off all the pixels in one go.